today I will present our work that has a very long title, but in general revolves around class fitting in residual networks. That was accepted for this year AAAI conference. So this is the joint work done with Marcin Kudziel, my colleague from AGH, University of Science and Technology. Okay, so the schedule for this presentation is as follows. First, I will present some general considerations. Later, I will familiarize you with some technicalities, and finally, I will describe our experiments that we did as a part of this work. So, our main motivation in this work is a desire to get a better understanding how neural networks internally represent classes. So, basically, we want to formalize a notion of class representation in a neural network and use this notion to characterize representations of classes. So to uncover an interesting structure that might be present there. So obviously the first step toward this goal is to formalize a notion of class representation in neural network. And now it's not a trivial task because classes are inherently related to sampling of class members from the data distribution. So in other words, simply speaking, we are dependent on what we observe in our training data set. And then a reasonable notion of class representation should capture the outcome of this sampling. So in this work, we propose to leverage class-conditional distributions of neural representations as proxies to representations of classes in neural networks. So to be more precise, we fit tractable class-conditional density models to sets of neural representations, and we then use these models to characterize distributions of representations of classes. So surprisingly, find that classes are not fitted in a uniform way. On the contrary, our models uncover distinct modes of something that we called distinct modes of class fitting in residual architectures. And we show that it has important practical consequences. So that is, we show that distinct modes of class fitting correlate with memorization of input examples and robustness to adversarial example. Okay, so everything I said so far might sound a bit vague. So after this brief introduction, let me present our work result in more details. So the first thing is I talk a lot about neural representation, but let me explain what do I mean by that. So in many contemporary architectures, the input to the classification head is constructed by pooling activations across spatial dimensions. And we use a similar construction here. So we form neural representations for inputs by applying an average pooling on the convolutional volume at the stage of interest because we analyze these representations at different stages of the network. So this way, for each input, we obtain a vector of activations, and this is basically our neural representations for that input at a given stage. Now, we want to construct class-conditional density models. So after obtaining the representations from the whole data set, we split them according to class labels. And we fit a separate density model to representations from each class, and this gives us class representation. Okay, now let me tell you a few words about the models that we use in this work. So the model is a very standard one, so it's a mixture of Gaussian with the unknown number of components, and this is usually called the Dirichlet process mixture model, as we put the non-parametric prior over the parameter space. And this is the model that we have already used in our previous work, where we were comparing networks that were forced to memorize the input data set and networks that exploited patterns in data. And now we extend this line of research to class-conditional models to representations of classes. So just to give you an illustrative example how this model works. So imagine that we observed some data points. And in our case, these are representations, and basically this model explains these data points with Gaussian components, and the number of the components adapts to the data. And this is the Bayesian model. So those of you who know the Bayesian approach to learning know that learning is not about optimization, but about doing the inference. So as an outcome, we have the so-called posterior distribution over parameters of this model, and we can combine this. Posterior distribution with the likelihood to obtain something that is usually called a posterior predictive. And now, importantly, in our Dirichlet process Gaussian mixture model, we can estimate the divergence between this predictive distribution and another distribution that has a tractable density. And we can use it to measure the complexity of the estimated density. So let's take a look at the plot. So what happens here? We have our estimated density, right, estimated on some data set. We also fit a much simpler model to the data, say, least assumption distribution. And then we estimate the divergence or relative entropy between this predictive posterior density in this simpler model. Okay, so the question is now, what is the least assumption distribution here? So in this work, for the least assumption distribution, we use so-called maximum entropy distribution that explains just the location and the scale of the data. And if you consult any textbook on probabilistic machine learning, you will find the proof that the distribution that has the highest entropy, assuming its first and second moment, is the Gaussian distribution. So basically, our least assumption distribution is a Gaussian with first and second moment estimated from the data. So the complexity of the predictive posterior is basically the divergence from the Gaussian into our predictive posterior, which has a functional form of a mixture of students T distribution. Okay, so we use this complexity measure later, so I wanted to explain it in more detail. So this is basically the machinery that we use to characterize the representations of classes. So let's move to what we found out with this machinery. And we begin our analysis by comparing log densities estimated for inputs from each class. So here we see log densities estimated for representations from ResNet 50 network that was trained on mini ImageNet dataset. And here we plot the mean and standard deviation for each of the class. The mini ImageNet counts 50,000 examples, around 500 examples per class. So basically for each class, plot the mean of its log densities and standard deviation. So classes on y-axis are sorted according to increasing log densities. And in the initial stage of the network, there is nothing unexpected to speak of. However, in a deeper stage of this network, we suddenly see two markedly different groups of classes, and they differ in mean log densities and also in the variance of the estimated density. So basically, we observe low density classes on the left and high density classes on the right. And this is quite interesting, and we obviously repeated this experiment with another ResNet architecture. This is for ResNet 50. We obviously repeated for ResNet 18 and another data set, C400, and observed the same phenomenon. So an obvious explanation for that would be that high density classes are simply more packed in the space, are more compact. That is, representations of these classes are more similar to each other. But our results show that this simple explanation is incorrect. And basically here on the plot you see that these blue dots, and for each class we calculated the mean intra-class distance between activation vectors of examples from this class. And these are these blue dots. And as you can see, there is no difference in span between low density classes and high density classes. However, if we look at the complexity of class-conditional distributions, so here we use the measure that I described to you before, we see that high density classes are vastly more non-Gaussian, which means that these distributions are very multimodal, or roughly speaking, they have many components. So the question is how we can reconcile these observations. So it appears that in high density classes, probability mass is concentrated in compact but spatially distant, spatially separated components. And as I will show you later, it has some significant practical consequences. But before that, let me note that what we observed is not just a byproduct of the data set that we used in our experiments, because we repeated the same experiment with a very simple, plain convolutional architecture that has 8 layers, which by layer I mean the sequence convolution, batch normalization, pooling, and nonlinearity. And here we basically display the same plots, log densities as before, but for the first layer and from the 8, for the first and for the last layers. And as you can see, there is no distinct modes of class fitting in plane convnets. Like everything is more or less similar. So obviously, the network architecture is important for the structure that we uncover. Okay, why these distinct modes of class fitting so important? And quite recently, Feldman and colleagues showed that the deep model that has to fit so-called long-tail data distribution, so the distribution which comprises many infrequent components, in order to minimize the generalization error, has to memorize some of the input example. And this is actually quite contrary to what people traditionally think about memorization, as they associate memorization with overfitting, and overfitting is supposed to deteriorate the generalization error. But Feldman shows that this is not necessarily the case. And in the subsequent work, Feldman and Zhang proposed a practical algorithm to estimate the memorization score for input examples of the data set. And we leveraged this algorithm as well in our experiments. But anyway, they demonstrated that contemporary neural nets memorize training examples to the non-trivial degree. And why this is important? So it might suggest that in high-density classes may correlate with the increased memorization because at the representation level, they appear to be formed from compact and spatially distant components. So basically, it makes harder for the network to find patterns there. Okay, and let's see what we observed here. So you observe that in the transition from low to high density regime, indeed coincides with increased memorization. But before that, let me explain what you have here. So we assigned neural representations to beans with increasing class-conditional log density. So in total, we have 50 beans. And on the left, we have examples with lowest log densities, and on the most right, we have a bean with examples with highest log densities. And for each bean, we also show the memorization score of the input examples, as this is this red series. So initially, when the log density increases, memorization decreases. And this is expected. As representation we are moving from outliers to more typical examples, and representations simply become more similar to each other. However, once we transition to high-density classes, once we transition from low to high-density classes, we see that the memorization score abruptly increases and later remains constant. So what conclusion we can draw from it? There is increased memorization in high-density classes, and it might have its consequences, for instance, in differentially private learning. Okay, so another aspect of neural networks where these high-density classes may play a role is so-called robustness to adversarial attacks. So robustness to adversarial attacks means how easy or how hard it is to perform the adversarial attack on a given input. So why it might play a role here? So in particular, spatially separated components in high-density classes should intuitively be less robust to adversarial attacks, as any small perturbation applied to the input can move the representation outside its component and most likely move it outside its class. So one way to verify this hypothesis could be to compare examples from different classes and with respect to susceptibility to adversarial attack, which would basically mean that we run a wide range of adversarial attacks. But because nowadays there are so many different attacks that each having its own characteristic, that we decided to go the attack agnostic way. So in other words, we decided to leverage a very nice branch of research called the certified robustness, which aims to provide theoretical guarantees that a given classifier in some surrounding of the original input won't change its predictions. And we particularly use the randomized smoothing-based certification procedure that was proposed by Cohen and colleagues, and we compare low and high density classes with respect to the F1 score of the smoothed classifier. So basically, they propose a certification procedure that aims to predict the class for the given example, as well as compute the certification radius around the given example, that with a certain confidence, we are sure that the smoothed classifier, the classifier won't change its prediction there. Okay, and so we compare low and high density classes with respect to the F1 score of the smoothed classifier and also the certification radius. And let me show you what we have observed. So again, in this transition from low to high density classes, we see that the performance of the smoothed classifier drastically drops. This certification procedure may also abstain from returning the class, and we also display it here, and basically this abstain ratio is slightly higher for high density classes. So, in other words, high density classes appear to be less robust to adversarial attacks. Okay, and I'd like to summarize my talk and what we have found out. So surprisingly, we found that classes are not fitted in a uniform way. In residual networks, we find so-called distinct modes of class fitting. And this is also interesting from the other perspective, because quite recently, it has been shown that as training progresses, and it progresses for a relatively big amount of epochs, classes became increasingly more separated. So it means that intra-class variance, comparing to between-class variance, basically becomes close to zero. And this effect is called the neural collapse. And our result shows that despite this neural collapse, classes in residual networks still retain the non-trivial internal structure. And this structure is not explained just by the data sets. Definitely the architecture plays a role here. And furthermore, these distinct modes of class fitting also correlate with input memorization and adversarial robustness. So this concludes the presentation. So here in the presentation, I have shown you only the fraction of our results, the most important ones. But in the paper, we include also much more. We include some initial results for vision transformers and MLP mixers, so non-convolutional architectures. And I encourage you to see the paper. So this is it from my side. Thank you for your attention, and if you have any questions, I will answer with pleasure.